Hello everyone. We already have started discussion regarding different circuits associated with sensors, and recently we have discussed instrumentation amplifier, which is again very important as far as the sensor signal amplification is concerned. Apart from amplifiers, there is another very important component of sensor system, which is known as filters. So as far as the amplifiers are concerned, we already have seen a variety of amplifiers and how we can use those amplifiers in different situations, and at the same time how these amplifiers work, that also we have briefly have seen. Now today let us start the discussion regarding filters. As I have said, this is again a very important component of sensor system, because in many cases you may need to filter a portion of signal, or you may need to filter signals beyond certain frequency range or below certain frequency range in order to make the system reliable. One such very common example is, you may always probably seen that once you start working with the different electronic component, you may figure out that there is a noise signal associated with nearby electrical and electronic equipments that usually hampers the working of the sensor system that you are developing. During experimentation also, when you characterize sensors, you may come across such type of problems. In those cases, it's very important that you actually avoid those noise components when you are measuring sensor characteristics or when you are integrating the sensor with the system, because the system has to be reliable. So in this line, let us see what are the basic filters associated with say sensors or analog electronics for that matter. So in this case we have 4 different filters. First one is low pass filter. From the name itself, it is very clear that the filter will allow low frequency signals up to a limit. For example, say in this case, if it is in this case it is FH. So if you have a signal having frequency less than FH, then this filter will allow that signal to pass through. Anything beyond that cannot pass through that particular filter. So that's why we call it low pass filter, because it allows low frequency signals to pass through it. The second type of filter is high pass filter. Again, from the name itself, it's very evident that this filter will allow frequencies beyond certain cutoff frequency. So in this case, say FL is your cutoff frequency. Any signal having frequency more than FL will pass through this filter. Okay, so this is the plot for the same. Then we also have band pass filter, where this filter will allow a particular band of frequency to pass through. Anything beyond that or below that will not be allowed to pass through. So in this case, let us take 2 frequencies, F1 and F2. So if there is a signal which has a frequency between F1 and F2, this can pass through this filter. Anything below this F1 will not be able to pass through. Anything beyond the frequency F2 will not be able to pass through. So only frequency or signal with frequency between F1 and F2 can pass through this filter. Similarly, we have another 4th type of filter, which is known as band reject filter. It's just opposite to band pass filter. So in this case, in case of band reject filter, this filter will only allow or restrict a band of frequency. Anything below or beyond that band can pass through that filter. So here again we have taken F1 and F2 as 2 frequencies. Anything below F1 can pass through this filter. Anything beyond f2 can pass through this filter, but if the signal frequency lies between f1 and f2, then the filter will not allow this frequency to pass through. Anything below f1 can pass through, anything beyond f2 can pass through. Anything between f1 and f2 will not be allowed to pass through. So these are the 4 basic types of filters. Then we also have another filter which is known as all pass filter. So in this case, the filter allows all the frequencies to pass through, but it has a different application altogether, because if the filter is allowing all the frequencies to pass through, then what is the need of that filter? So there is a need of this kind of filter, which is again defined, but mostly you will find that in many of the sensor systems, these are the 4 types of filters that are in use. So usually filter is an analog component, but you also will find digital filters. If you go through signals and systems and digital electronics, you'll find there are different digital filters as well. But in general, filter is kind of a analog component. Usually we use filters for analog signals, but as I have said, you may also find digital filters in different other subjects. In this case, we will discuss about the analog filters. Okay. Now, filters again can be divided into 2 different parts. One is active filter, another one is passive filter. Okay. So active filter will have an active component associated with that filter circuit, and passive filters are made of passive components. So let us start our discussion with the very basic filter, that is the low pass filter. But before we go to that discussion, let us see what is the difference between ideal filter characteristics and practical filter characteristics. So in this case, I have shown you 2 different plots. The first plot is the plot here is the characteristics of a low pass filter. So ideally, the low pass filter characteristics is something like this, that we also have seen in the previous slide. But in practice, you will see that the response of a filter is like this. So it has a ripple, and then it slowly transit to almost 0, and then again you will see another ripple present in this direction, the right hand side as well. So these ripples are kind of practical cases. To make our discussion or to keep the discussion simple, what we do is we consider that all these ripples have a single frequency. It's a single frequency ripple, and hence one can see that every filter has 3 different zones. One is pass band, that is this area, where the filter will allow the frequencies to pass through that. Then we have a transition band, where the filter characteristics will move slowly to 0, and then you have stop band. So in stop band, no signal is allowed to pass through. So we have 3 different zones: pass band, transition band and stop band. In ideal case, we don't have this transition band present. So it's like a sharp cutoff from a certain frequency. At particular frequency, the signal will drop to 0. Okay. So that is what everyone will try to achieve. Everyone will try to achieve this type of ideal characteristics, but the practical situation is something different. So you will always see a transition band present, and then we don't also want this ripple to be present in the filter characteristics, but you will see in practice there are ripples present. So ultimately you'll get a characteristics which is something like this, and then it is coming down, and then this. So instead of these characteristics, you have a characteristic similar to this one. So it will have a characteristics similar to this one, where it has a pass band, a transition band, and a stop band. In case of band pass filter also, you have two stop bands, and then you also have two pass bands, and you have two stop bands, two transition bands, and one pass band. Okay, I repeat, in case of band pass filter, you have two stop bands, one lower, another one upper. So you can say it as a lower stop band, upper stop band. Then you have two transition bands, both towards lower frequency side and higher frequency side, and then you have one pass band, right? So this is what characteristics of a band pass filter will look like, and this is the characteristics of a low pass filter. Similarly, you can now imagine how the characteristics of a high pass filter will look like in practical situation, and also you can think of characteristics of a band reject filter, right? So this is something one should understand, that in practice the situation is not same as what we have discussed in ideal case. So before again we go to the sensor filter discussion, before we start that discussion, we also should know what is transfer function of a network. Why we are discussing this? Because once you have that idea about transfer function, then it's very easy to realize the filter characteristics. We also call it S domain analysis, because we convert j omega we replace j omega with S, so that's why it is also called S domain analysis. And if you look at a system, you can see it's a two-port system, of course. So in this case, you'll see that your input and output can be any of these combinations. So this can be like voltage and voltage, that is input voltage, and output also is voltage. You may find the input is current and then output is also current. You may find your input is voltage, output is current, and you also may find that your input is current, output is voltage. So all four possible combinations are there. However, as far as the transfer function is concerned, transfer function is the ratio between your output and input. And you also can define it with this equation, where k into s minus z1, s minus z2, z2 till s minus zn divided by s minus p1, s minus p2, s minus pn is the representation of your transfer function. So this is true for most of the situations, most of the cases. However, we will also take the help of transfer function in our circuit case. Okay, it's not very specific to circuit. You will find transfer function of different other systems as well. However, in this case, we will take help of the transfer function in order to define our systems. So in this case, Z1, Z2, Zn, these are known as zeros, and P1, P2 till Pn, these are known as poles. That is how we define it. You probably have studied poles and zeros in your analog circuits. However, just to recap the entire discussion, I am showing it here as well. So if your S is equal to any of the zeros, maybe Z1, Z2 till Zn, if it is equal to any of the zeros, in that case your transfer function will be 0. However, if your S is equal to any of the poles, then your transfer function will tend to infinite. So this is the basic discussion regarding the transfer function. Okay. Now let us see a low pass filter. So let us start with a passive low pass filter, which is shown over here, although it is written over here active networks, but let us start with a passive circuit first, where you have a low pass filter. It's a low pass RC filter where R is a resistor and C is a capacitor. This is connected the way it is shown over here. This is your input voltage, this is your output voltage. Now, if you figure out the transfer function associated with low pass filter, that is V output by V input, which is HS. HS is the transfer function. Now, V output can be given by 1 by CS, and in case of V input, it's 1 by CS plus R. So, if you rearrange that equation, it's 1 by 1 plus RCS. You rearrange this equation further, so it's like 1 by 1 plus S. So, in this case, you have a pole 1 by RC. That means at certain frequency, you'll have a pole, and hence the plot will start decreasing with a slope of 20 dB per decade. So, in this case, your plot is decreasing with a slope of 20 dB per decade. So, if you look at this particular characteristics, it's nothing but a low pass filter, because beyond certain point, signal will not be allowed to pass through. So, here this is your transition band, right. So, beyond this point, the signal will not be allowed to pass through. That means this is a low pass filter. Similarly, the corresponding active network is something like this, where you have connected the circuit with a voltage follower. Now, if you add some resistance or passive component here, you will also be able to get some gain from this circuit. That's why it's called active network. So, here the op amp is your active component. So, the corresponding active low pass filter is something like this, where the entire filter is connected to a voltage follower. Now, once you connect it to a voltage follower, you don't get a gain, but the active network, that means this voltage follower will help you to decouple output from input. Okay, that decoupling is possible if you add an op amp as a voltage follower here, and you also get an extra advantage. If you add some passive component over here, you will get a feedback, and hence you will see that the signal also is getting amplified. So, these are the extra advantage that you get in case of active networks. Similarly, this is the circuit for an high pass filter, again with passive component with RC circuit, RC network. In this case, your transfer function, that is V output by V input, is something like R divided by R plus 1 by CS, that is RCS divided by RCS plus 1, and this will give you a 0. Now, if you have a 0 and also a pole at the same point, that is 1 by RC and 1 by RC, right, both pole and 0 is at a single point. So, the 0 will help you to increase the response at 20 dB per decade. The pole will at the same time try to reduce the response at minus 20 dB per decade, and as a resultant you will see a constant response. So, in this case you have a response which looks like this plot. That means that beyond certain frequency you will see that the filter is allowing the signal to pass through. That means this is an high pass filter. Similarly, the corresponding active network is something like this, where you connect the filter with an voltage follower circuit as it is shown over here, and this also can act as an amplifier if you add a feedback over here, right. So, if you look at the low pass filter and high pass filter, it's nothing but just replacing R with C and C with R. In case of low pass filter, you have a R in here and C in here. However, in case of high pass filter, you have just replaced the R with C and C with R. So it's as simple as that. Okay, and then you will find corresponding characteristics as it is shown over here, right? Now let us also check a generalized two-pole active filter. The purpose behind discussing the generalized two-pole active filter is you will be able to get an idea about a generalized filter, and then when you want to design a filter, you can just replace these generalized components, and then you will be able to figure out your, or you will be able to design your own filter. Now in case of generalized filter, as it is shown over here, y1, y2, y3, y4 are 4 different components, where y is equal to g plus jb, which is nothing but reciprocal of z, that is impedance, r plus zx, that is how we define. But if you express the entire circuit in terms of y, the equation looks much simpler. That's why we are expressing z with, or z in terms of y, but it's just the reciprocal, right? Y is equal to 1 by z. Now you have few nodes over here. This is the input. Then you have VA. This node is termed as VA. This node is termed as B. That means the voltage here is VB. This is the node A, where the voltage is VA. This is the node B, where the voltage is VB, and this is your output VO or V0, whatever you say, right? Now in node A, if you write the equation, it's nothing but V in minus VA into Y1. It's actually V in minus VA divided by Z1 if you replace Y1 with Z1, right? Now 1 by Z1 is Y1, so that's why we wrote V in minus VA into Y1 is equal to VA minus VB Y2, that is VA minus VB Y2 plus VA minus V0 Y3, because the current will go in this two direction. So the current here is a summation of current in this loop and the current in this direction, right? So that's why we have written the equation like this. This is your equation 1. Similarly, in node B, the current is VB minus VA into Y2 is equal to VB minus 0 divided by Z4, that is VB minus 0 divided by Z4, which is nothing but VB into Y4. That is what it is written, and we know that no current flows inside the op-amp. So this is your equation at node B, and in this case your VB is equal to V0 because this is connected with a voltage follower. So the input and output should be equal. Now if you take these three equations and rearrange this equation, you will find that your V output by V input, that is the transfer function, is something like this: y2 y1 divided by y1 y2 plus y1 plus y2 plus y3 whole into y4. So that is what is your transfer function. Just rearrange these equations and you will be able to figure out the transfer function associated with this filter. Now this is kind of a semi customized solution where you can change the values of y1, y2, y3, y4, and you will figure out, or you can get your desired transfer function, right? So this is a generalized two-pole active filter example. Now let us take an example where we have taken different components in place of y1, y2, y3, y4. So this y1 is replaced by a R1, a resistor R1. Similarly, y2 is replaced by a resistance R2. y3 is replaced by a capacitor C3 and y4 is replaced by a capacitor C4. Just put, and we know that the transfer function is V out by V in is equal to Hs into Hs, that is equal to y1 y2 divided by y1 y2 plus y1 plus y2 plus y3 into y4. Just put the values of y1, y2, y3 and y4 in this equation, and you will be able to get a transfer function similar to this. Now, in this case, if s is equal to 0, then your hs is equal to 1. If s is equal to infinite, then your hs is equal to 0. That means this is kind of a low pass filter, right? So, if your s, the value of s is 0, then your hs is 1. That means if your frequency is in the lower frequency domain, then you have the transfer function value as 1. If it is in the higher frequency domain, because if s tends to infinite, that means omega also tends to infinite, then your transfer function becomes 0, right? So, in the low you have some value, in the high it will go to 0. That means it is a kind of low pass filter, and this is an example of Butterworth filter. Okay. So, in this direction, I would just mention what is a Butterworth filter. Butterworth filter is a special kind of filter where you will get the ripples to be minimized. So, the purpose of Butterworth filter is to reduce the ripples present in the transfer function or present in the circuit, right? And similarly, we also have another filter which is Chebyshev filter. The purpose of the Chebyshev filter is to reduce the pass band. Then only you will be able to achieve the ideal characteristics. So, ideal characteristics is something like that, but in practice you will have a ripple. So, just to reduce the ripple, you can use a Butterworth filter so that you can achieve this type of characteristics. And then in practice you also find a kind of transition band. So, just to reduce the transition band, we can use Chebyshev filter. So, I am not going in details of these filters because the idea or the purpose of this lecture is to provide you the basic understanding regarding the filters. So, that is why I am not going in details or in that discussion. So, in the upcoming discussion, we will discuss the summary associated with this course. We are almost at the very end of this course, and in the upcoming lecture, I will provide you some experimental idea about what we have discussed right now and how these circuits actually help. And then we will summarize or conclude the course. Till then, thank you.